So the first presentation of the year in BC Calc is going to be the tangents and velocities. I want to develop an understanding of what tangent means, but to do that we're going to start out by talking about a secant. A secant you recognize as a term probably that you've run into in trigonometry. But we're also talking about a secant line, so I'm going to write the word line right underneath here. And the meaning of a secant line, this is a line that intersects a function. At 2 points. So, if I have a function that looks something like, let's give it a x squared-ish kind of a look to it, and I draw a line that goes like this. This red line that I've drawn is a secant line because it intersects this function at 2 points over an interval that starts at some x value, maybe we'll call it x1, and ends at another x value, let's call it x2. Now if I take the slope of that secant line, the slope of the secant line between the points where we have x being x1 and x being x2, the slope of that gives you the average rate at which this green function is changing over that interval. So slope of a secant is an average rate of change. And those of you who have taken AD, well, you realize that that's something that you will not only be asked in September, but you will be asked for an average rate of change when it comes to May. And same thing is going to be true in BC Calc. Average rate of change is the slope of a secant, the slope between 2 points on a function. Now tangent. A tangent, and again, we're talking about a line here. And this is a line that intersects a function at 1 point. And again, you probably recognize this term more from trigonometry than you do from anything else. And I've got this line sitting here. I think you do in your notes as well. So if I were to draw a function that looks like this, kind of like what we had before, that would be a secant, wouldn't it? But if I take this line and I move this line, can I move this line? Come on, line, move with me. So that we just touch at 1 point. Now all of a sudden, this becomes a secant line, a tangent line. It just intersects at the 1 point. And if we find the slope of this tangent line, that's going to give us not the average rate at which the green function is changing, but it's going to give us the instantaneous rate at which this function is changing. The y value is changing with respect to x. At this particular moment, at this particular instant, at this value of x sub 1. So that's the difference between an average rate of change and an instantaneous rate of change, which again is not only important here in September, but is going to be important when we get to May. And our understanding of the term velocity. Velocity is a very specific slope. Velocity is a slope of a position time graph. That's what we're going to start out with our understanding of velocity being. So if we've got any kind of a, let's see, this would be the position, and this would be the time. And if we have some kind of a position-time relationship graphed here, whether we're talking about the slope of a tangent or the slope between 2 points on here, where we're finding the slope of a secant, any kind of slope you find from a position-time graph is going to give you a velocity. Maybe an average velocity, if you're asked for the slope between 2 points, or if you're asked for the slope at a single point, well, that would be the instantaneous rate of change, the instantaneous velocity. So that's going to be our understanding of velocity. Now here we're going to need a calculator. And we're going to be pressing the pause button a little bit here. We're going to find the equation of the tangent line to y equals x squared at the point 1, 1. Okay, good. Slope of the tangent line. Now we could have slope of a secant line. I could go from like 0, 0 to 1, 1. Something looks sort of like that. Now, I could find the slope of that line real easily because I have 2 points, so I could certainly find the slope. I know what the y-intercept is, so I could write a slope-intercept form of the equation of the line. However, that would not be the equation of the tangent line. So, let's work on finding the equation of a tangent line. And in order to do that, it says let's use calculators. Let's find the slope of point PQ. Now P is the point 1, 1. Q is going to be some other point. And so I'm going to give you those x values. You find the y values. And so if we know that y is equal to x squared, and these are our x values right here. Let's figure out what these y values are. Let's figure out what these y values are. Okay? So, you take a calculator, realizing that y is x squared, just square the x's and put those values in the y column. And then we'll come back. All right. These are the y values I got when I squared those x's. Now what we're going to do is we're going to find the slope of the secant. We're going to find the slope between the point 0, 0 and point P, which is the point 1, 1. P is always the point 1, 1. So if I find the slope between 0, 0 and 1, 1, I take y2 minus y1 over x2 minus x1, and I get 1. Okay, let's find the slope between 0.5, 0.25 and 1, 1. And I take my y2 minus y1 over x2 minus x1, and I get 0.75 over 0.5, and I think I get 1.5. Well, let's keep finding these slopes. Let's press pause. Let's keep finding the slope between 1, 1 and each one of these ordered pairs. And let's see what we come up with. All right, those are the slopes that I came up with. These are all slopes of secants because it's always the slope between 2 points. This point and, for example, this point down here. Now, of all of these slopes, we got to come up with the slope of the tangent line. And we said, you know, this one right here, that secant really doesn't represent the slope of the tangent very well. But if we choose a point that's much closer to 1, 1, if we choose something right here and we draw that little segment, does that look like it's pretty darn similar to the slope of the actual tangent? So if we find the slope between 2 points, the average rate of change, the slope of the secant, between 2 points that are very, very close, what we're going to find is a pretty good estimate for the slope of the tangent. And so as I look at my table, what's pretty darn close to the point 1, 1? Well, that would be this point down here. That's pretty close to 1, 1. And this point right here is pretty darn close to 1, 1. And the slope of the secant just prior to 1, 1, 2 points very close to 1, 1 just prior to it, and the slope of the secant just after 1, 1. What does it look like these slopes right here are getting pretty darn close to? And if you said, you know, the slope of that secant line, pretty darn close to 2, I think that would be a really good estimate for the slope of our tangent. So as I write the equation of my tangent line, the equations of lines in slope-intercept form in this case, I think the slope is 2. So y equals 2x plus, now I need a y-intercept. To find the y-intercept, you always plug in a point that you know is on the line. Well, I know 1, 1 is on the line. So a y value of 1 times an x value of 1 I think we can agree that's going to be -1. And as you look at this tangent line, doesn't it look as if it's going to go through -1? So by finding secants of points very, very close to that point of tangency, we can come up with the equation of the tangent line, which is an important skill. Suppose the data in the margin here comes from some scientific experiment. Y is a function of x. Draw the graph of this function and estimate the slope of the tangent when x is 0.2. Okay, I'm going to press pause, you press pause, you plot those points. I will tell you this, before we plot these points, that this is a y value of 0. 2 dots up, that's 0.1. 2 dots up is 0.2, 0.3, 0.4, and hold on a second here. Okay, I goofed up. I was putting the x values on the y. So I got my x values, obviously, on the x. 0.1, 0.2, 0.3, 0.4, 0.5. Now on the y's, we got to get up to 4. So this is going to be 2 dots up is 1, 2 dots up is 2, 2 more dots up, 2 more dots up. Now let's plot those points. Sorry about that. Let's press pause. Plot some points. So if I were to plot the points, I think they'd look something like that. And that would give us, we're going to connect those guys. Some kind of an arc that goes like that. So what do you suppose the slope of the tangent line at point 2 is? Well, if you are given a table of values, I want to tell you how calculus, how James Stewart, the author, is going to want you to find the slope of the tangent line. You could very well draw a tangent line that goes through point 2. Adjust that accordingly and try to figure out what the slope of that guy is by estimating some points. But what James is going to want you to do is James is going to say if you want the slope at point 2, you use the point just prior to it and the point just after it. And that is going to give you the best estimate for the slope of that line. So if I take the point 1, 3.71, and the point 3, 3.02, see y2 minus y1, yikes, negative, I think it's 0.69, divided by x2 minus x1, 0.2. Definitely a negative slope. Negative 3.45. I think that's accurate. So that's how we would estimate, and that's all they ask for. Estimate the slope of the tangent line. Yeah, we could draw the tangent line, but probably better, and a technique that you'll be expected to use is to use the points closest to that point of tangency, one above, one below. Use those to estimate the slope of the tangent. Now a ball is dropped from the top of a tower in Toronto. Boy, somebody's having a big time with those bells today. The top of this tower is 450 meters above the ground. Find the velocity after 5 seconds. Well, now, there's some information that just hasn't been given to you here. And that is, what's the position of the ball? What is the height of the ball at any moment in time? And the height of the ball at any moment in time, if we're dropping a ball from the top of a 450 meter tall building, is negative 4.9 p squared plus 450. So that was a formula that should have been given to you. Now let's estimate the velocity after at the 5 second mark, not after, but at the 5 second mark. Well, velocity is the slope of a position time graph, and here's the position and here's the time. And I want it at an instant, at that instant of 5 seconds. Well, what we just found in the previous example is we've got to use some points that are really close to 5 seconds, one just before and one just after. So how about if I find the height at 4.99 seconds? Figure out what the height is. And let's find the height at 5.01 seconds. Those are some points that are pretty darn close. One before and one after 5 seconds. Let's use this formula to find the heights and then find the slope between them. Press pause and do that. Okay, so here's what I got as my positions, my heights. Now if I take y2 minus y1, I think I get negative 0.98. And I divide that by x2 minus x1, or t2 minus t1. And I think if I do this correctly, I'm getting negative 49. And if I want to have some units with this, which I think I can have, because I know that this height is measured in meters. And so I found the change in height, which is measured in meters, divided by this change in t, and t is time measured in seconds. So I think it's negative 49 meters per second. And it makes sense that it's negative. Negative refers to the direction, and this thing is indeed falling down, so we would expect a negative value. Yeah. So that's how we're going to use slope of a secant to estimate slope of a tangent. And if that secant tangent involve positions and times, well, then those are going to be velocities. We're going to have easier ways of doing this, as you guys know who took AB. I mean, we're going to have a lot easier ways of doing this as the year goes on. But the meaning of what secant is and average rate of change, knowing the meaning of a tangent being an instantaneous rate of change, those are introduced in this section. And so it's worth our while to go through the more difficult ways before we get to the easier way of doing this. All right, that's section 1.4.